Okay, let's begin our workshop. Hello, ladies and gentlemen. Welcome to MICCAI workshop. Thank you for participation in the Ultrasound Enhancement Challenger and attending the workshop from all over the world. Now it's the morning for Vancouver and night for most Asia countries. It's my honor to host this workshop, and I will briefly introduce the challenger. Next page, please. Yes, thank you. Due to the non-invasive and real-time imaging, medical ultrasound is widely used in clinical, including helping disease diagnosis and treatment. Recently, medical ultrasound shows perspective in revolving from expensive big-size machines to economical handheld device. The barrier is that ultrasound examinations with a handheld device has the drawback of low image quality due to the hardware limitations. The left is the ultrasound images collected by a handheld device, and the right images are collected by a big-size machine. They are from the same patient at same location, but with different machines at the carotid artery, normal breast tissues, and breast cancers, respectively. Visually, of course, the right high-quality images can provide more details for doctors to diagnose. Toward this, ultrasound image enhancement provides a potential low-cost solution. Restoring high-quality images from low-quality ones can, using the artificial intelligence algorithms, could exploit requirements for hardware improvements and promote ultrasound device revolutions and wider applications. We hold the Ultrasound Enhancement Challenger in conjunction with MICCAI2023. The challenging task is to reconstruct high-quality ultrasound images from low-quality ones. We've collected virus data of 5 organs from different devices. A total of 3,000 ultrasound images, including 1,500 pairs from 109 patients, were provided in our dataset. The challenger is jointly organized by Fudan University, Shanghai University, and Fudan University Shanghai Cancer Center. It is also technically supported by the vinyl technology. There were 434 teams from 27 countries and regions participated in our challenger. Thank you for your active participation. Now please allow me to invite all the teachers and the students in the Zoom to turn on your camera and let's take a group photo together.
I will briefly introduce motivation and data, but I think I'm going to skip this. And then I will present our method. We basically set cyclogen as our baseline model. First, we attach classification head to cover multi-domain. In addition, we used high-quality reconstruction model to resemble the high-quality characteristics. Finally, we try to do fine-tuning strategy. At the end of my presentation, I will show you our results and the future works. Yeah, let's look at our method. Our method consists of 4 parts. First, cyclogen architecture as our baseline model. Second, the classification head. Third, cosine similarity using reconstruction model. Last, fine-tuning strategy. First of all, we simply set cyclogen as our baseline model because the training data is unpaired. Basically, we mostly implemented our baseline model, which one paper designed. The paper maintained that to stabilize the training process for receipt continuity, they added spectral normalization layers to discriminators, but in our case, the spectral normalization was not effective. So we just removed it. Instance normalization is mostly used at the generators. To handle multi-domain issue, we simply attach the classification head to the generator for high-quality imaging. We assume that each class has its own low and high-quality characteristics. Therefore, we thought that we trained the model to classify each class simultaneously. It would try to consider the image characteristics of each class. And second, to make better to generate high quality characteristics, we made use of a high reconstruction model. We assume that a high quality reconstruction decoder would be better able to capture the style information of high quality images. So we tried making high quality generator decoder similar to high quality reconstruction decoder. To do this, we first trained high quality reconstruction model, which has the same architecture with high quality generator network. And then we extracted each of decoder feature map and then compared it. To be specific, we freeze reconstruction model. So the high quality decoder try to resemble the reconstruction decoder's characteristics. In other words, we hope to distill reconstruction analogy for making the high quality generator better. In detail, we first extracted each of feature maps from intermediate layers of decoder, and we considered a feature map of the reconstruction as label and a feature map of the high quality generator as prediction. Channels in the same position are independent variables. Channel-wise cosine similarity is applied to make the channel's information of a high-quality generator decoder to reconstruction decoder. And after our model training our model, we simply added PSNL loss for fine-tuning. We just assumed that if we train to many tasks from the beginning or scratchy, the gym learning model will struggle to find the optimal solution. So we first tried fine-tuning suboptimal solution and then adding specific metric task loss like PSNL loss. Here is our experimental results. When we separately applied classification and cosine similarity strategy, the result was worse than our baseline model. But when we simultaneously used both classification task and cosine similarity, all metric results were improved. At the fine-tuning strategy, the added PSNL loss also had good influence on all metrics results. This is our discussion and future work. First, we will design various classification tasks. In this experiment, we just classified 5 classes, but one class seems like to include heterogeneous structures. So if we well designed classification task, we expect that the result could be better. We can also use 6 residual blocks featured for other like the kind of auxiliary laws. And second, reconstruction model can be reused for an image enhancement. We watched reconstruction model decoders can be used for high quality generator. This means that the reconstruction analogy can be effectively distilled to the generator. So we need to find whether the better performance of reconstruction model can give a good result to the generator. If it's working, we will also try to use the reconstruction encoder analogy for using like kind of perceptual loss. Last, in this experiment, we just added PSNL loss at high quality generator, but we can try to add other or new loss for fine-tuning. Yes, this is our team members. We always hope to globally work for our research. If you have any questions and interest, feel free to email me. Yeah, our research is supported by many granting, so thanks for these supports. This is the end of my presentation. Yeah, thanks for listening. Thanks.
Thank you so much. That was very insightful and really a great start. Since we will have an individual Q&A session after our presentation finished, so please remember the presenter's order number if you have any question. Next, we have Seoul National University presenting their research and findings for the Ultrasound Image Enhancement Challenge 2023. Please.
Okay, hello. Can you hear me?
Yes, we can hear.
So I will start here.
But the voice may be a little bit small. Can you make a large?
Okay. So is the problem solved or?
Sorry, we cannot hear you clearly.
Can you hear me?
Yeah, it's much better.
Yes, sure. Thank you.
Thank you. Hello, thanks for the invitation for the event. We are Team MICCAI from Seoul National University, and this is our team member. These are our team members. Today, we're going to talk about our method. The problems we have to solve is to enhance the low quality ultrasound images to high quality ones. And we try to find the answers for the following questions. The first question is how to make a model when the trained images are not registered. The trained data we received was not registered, but the test data would be registered. The second is how to enhance multiple organs simultaneously with one model. We got ultrasound images, which consist of 5 classes of organs, and each class images have different shapes or textures. So we needed to train a model which can process 5 different classes of organs. And the last question was, what is a good enhanced image? We try to find the right loss functions to get the results, which were perceptually good. So this is our overall architecture of our model. Because of the first problem I just addressed in the last page, we chose CycleGAN as our base model because it is an unpaired translation model. And we followed the discriminator of CycleGAN, which had 7070 patch GAN. We have integrated our class feature extractor module into the CycleGAN generator to solve the question and improve our model. So the CFE module, we used deep clustering method to train this CFE module, and we used the process of deep clustering method to train the CFE module. First, we initialize an appropriate convolution network and fed the images through the CNN to extract CNN features and performed k-means clustering on the features and assigned pseudo classes based on the cluster numbers and trained the CNN for classification. Then we repeated steps 2 to 4 by fitting the images through the CNN again until the classification loss converges. So these are the clustering results of our class feature extractor. The clusters 4, 9, and 22 were well split by the organ class information as intended. And these are some more CFE provides more detailed information than just organ class information. So in the same thyroid images, the cluster 23 and 30 has different clusters based on the shapes of the images, but for a kidney and liver, the clustering method didn't distinguish between the organ classes. So this is our generator model, a CFVG. It is composed of head, tail, enhancement block, and CFV module. The head and the tail are the downscale and the upscale convolution layers following conventional cyclogen, and the enhanced block is a residual block. The class features extracted from class feature extractor module were added to the inputs and the outputs of enhanced blocks. For the loss functions, we used the base loss from the original cyclogen paper. And also, to train our CFE module, we try to include the pseudo-level classification loss. It's determined using pulse entropy loss, like a conventional classification test. We also added VGG-based feature loss for 2 reasons. First, we try to convey more of the low-quality images feature information to the generated images. Second, to leverage the pairing information between low-quality and high-quality images. So we used both forward VGG and cycle VGG losses here. So our total loss is defined as the linear sum of the base loss and clustering loss and VGG loss. This is our experiment results. We try to do some ablation study here, and the model with eight enhanced blocks, block and CFV module and VGG loss gave us best result. And now we want to show some results in images. So these are from train samples, and the images from the left are the low quality images, and the right is a ground truth image, and the middle is our result. Try to show the results in all of the organs. And the test samples, the left is the low quality image and the right is our So in summary, we modified the cyclogen to enhance multiple classes of ultrasound images. We use cyclogen because it is an unpaired image translation model. And the modifications we used is a class feature extractor from the clustering model integrated into the cyclogen model. The second, we try to use VGG loss, which combines both forward VGG and cycle VGG to make a better result. Thank you.
Thank you, great presentation. Thank you so much for sharing your work. Our third presentation will be from the Southern University of Science and Technology, offering a deep dive into their approach and findings titled Unpaired Structure Preserving Medical Image Enhancement. Please. Sorry. We can't hear you.
Oh, sorry. I muted myself.
It's okay. Please.
Okay, I'll begin again. Okay, I'm Heng Li from Southern University of Science and Technology, Department of Computer Science and Engineering, MIT Lab. The algorithm name of our algorithm is unpaired structure preserving medical image enhancement. And I'm going to introduce our algorithm in 4 parts. Okay, first is the description of our algorithm, and then I will present some experimental results. And I have some discussion about the algorithm we used here compared with the algorithm we developed previously. And finally, I will introduce my team. Okay, just as the algorithm the first 2 team used, we also used the structure of cycle GAN, but we use a more simple design that the same to a cycle GAN. We use the cycle loss and identity loss, which is composed of the transfer loss here in our network, and then what we changed is that for the translated image, we use the illumination loss and the structure loss here, which is to preserving the structures in the medical images. And here are some results. The first line is input images, and the second line is predicted results from our algorithm, and the last one is ground truth. And here are the quantified metrics of our algorithm, and the code of our algorithm has been published on my GitHub website. Finally, I want to have some discussion of the algorithm we use here, because at the first phase of this challenge, we use the paired image translation algorithms, which because our team was focused on fundus image processing, so which we are more familiar is that here I mean pixel level pairing images, just as I put here the fundus image, the noise image and the ground truth image are pixel level paired, which we can use just as such as pixel to pixel architecture to do some translation work, which I think it's has a boost to preserve structure image structures. That I think is very important in medical images. But actually, the paired image we use in this challenge is not pixel level paired. It's just as image level paired that I put here. They have similar structures, but in the pixel level, they are quite different to each other. So at the beginning, we used the pixel level paired algorithm. We suffered a lot about the result on the test data. So we translate our algorithms to the cycle GAN architecture and get the final results. Here is a team of our lab. Professor Liu Jiang is the director of our team, of our lab, and I'm the team leader of this challenge. And Lin Ziqing is a graduate student. Li Zina and Mao Chenyang are 2 undergraduate students of our team. I'm proud of them as they usually didn't do ultrasound enhancement. So thank you.
Thank you. Thank you. Really impressive work. So next, we will hear from Tongji University presenting their description of USenhance 2023 submission. Please.
Can you hear me?
Yes, we can hear.
Okay, thank you. Hello, everyone. I'm in great honor to give this presentation. My name is Liu Xinyu. Our team is Tongji iLab, and we come from Tongji University. I will talk about some of our work in USenhance challenge about ultrasound image enhancement. Let me open my camera. Okay. First of all, let me introduce our team. Our instructor is Professor Luo. Our team consists of doctoral student Li Bo, 3 undergraduate students Rao Ji, Hu Ruining, Meng Yuxin, and myself. The dataset used in the computation contains pairs of ultrasound images from of 5 different organs of the body. The upper row in the slide is low quality images, and the lower row is corresponding high quality images. Image enhancement requires the model to have strong capabilities to generate high quality images. We adopt data augmentation to increase the amount of data and improve the model's ability. Specifically, we used several traditional data augmentation methods and a random augmentation method called trivial augmentation. It can randomly sample a typical augmentation method and an integer as intensity. Then it will apply them to the image to get the result. We have also tried other auto methods like random augmentation and auto augmentation. Trivial performs best. The right images is several random results of the same input from trivial augmentation. When it comes to the method chosen, we tried multiple networks in the field of image reconstruction or generation. For example, the most typical reconstruction method UNITE. It can take an image as input and get a generated output with pixel level supervision. It's easy to realize and widely used, but can't work well in this task. Meanwhile, we attempt to use generative adversarial network to enhance the low quality images. The generator can generate new images with the information of low quality images. High quality images and generated images will send to the discriminator. The training process is an adversarial process between the generator and the discriminator. However, GAN can't get a satisfactory result, and the generator results differ significantly from high quality images. Afterwards, we tried a recent method called deblurring MIM. It adds some noise to the input and masks them, then generate a new image with an encoder-decoder architecture. In general, deep learning MIM performs well than UNITE and GAN, but the result is obviously blurry and the performance is not particularly good. After summarizing all the above methods and analyzing the dataset, we found the key to the problem. Most of the above methods are based on highly registered image pairs. In the training loss, there is mostly a pixel-wise comparison between the results and the ground truth. However, the dataset we use is not registered due to some angle deviations of devices or physical changes. You can easily find that there are positional difference between high quality and low quality images. And this difference cannot be eliminated by registration methods. Therefore, when we forcefully match image pairs, we will force the model to learn this randomly caused position of size. Under the guidance of this proposal, we turned our research direction to image domain transfer and choose cycle GAN as our method. This method can summarize the features of different image domains and transfer images from the source domain to the target domain. It consists of 2 individual parameters GAN. One of it transfers images from domain X to domain Y, and the other does the opposite. The detailed architecture of our proposed cycle GAN is over here. The generator contains encoder and decoder with convolution and transport convolution. There are non-residual blocks to extract image features. The discriminator is a simple convolution network as classifier. During training, domain X images is first transferred to domain Y through the generator J, and then the generated result is transferred back to domain X through another generator F. The original image X and the retransferred image X hat have cycle consistency. The definition of the loss function is over here. In the method we adopt, we use 4 loss functions. The generative adversarial loss is as the same as GAN. The cycle loss is produced from cycle consistency. The identity loss can be intuitively understood as when we input the image of the source domain X into the generator from Y to X, it should not change. The SSMM loss is designed to improve the structure similarity between generated images and target domain images. We have compiled the results of different methods on the test dataset. The values given are all from the leaderboard's results. As you can see, in the validation phase, the domain transfer method cycle GAN with trivial augmentation gets better performance than others. In the testing phase, we add 2 loss to cycle GAN and it achieves better result. Meanwhile, we found that the trivial augmentation performed poorly after adding the loss, so we removed it in the final commit. Shown here is a comparison of the results of enhanced images and low quality images of the final submission. It can be seen that the enhanced images contain more details. In summary, we use style transfer method cycle GAN to reconstruct low quality images to high quality images. However, our method actually doesn't require paired images in the process and wastes the paired information in the dataset. In future research, if a supervision for ultrasound paired images can be designed and added to the current cycle GAN, it may be able to achieve better results in ultrasound image enhancement. Here's a photo of our lab in Software School, Tongji University. That's all for my presentation. Thank you for your listening.
Thank you, Xinyu, for your great presentation. Next, the MICCAI2023 team from the Southern University of Science and Technology has impressed us by submitting 2 distinct groups of results. Now, other method using the cycle GAN ranked 5th. So next, MICCAI2023, you can proceed with your other presentation now, please.
Hello. Good morning. Okay, can you hear me?
Yes, yes.
Okay. Good morning. It's my honor to be here today to share my team's recent advance in medical imaging enhancement. Our research is based on the South University of Science and Technology within the Department of Computer Science and Engineering. We have been exploring an approach then pair medical imaging enhancement with G cycle GAN. As many of you are aware, obtaining unpaired medical imaging from training enhancement algorithm can be challenging. Our method inspired by the success of cycle GAN in other domains aim to address this by using unpaired data. So let's have a look at the agenda for today's presentation. I will deliver into the algorithm description and discussion, and finally introduce our team. So here we have a detailed look at our model's architecture. The network consists of a generator and discriminator. The generator can be further divided into 4 major components: an encoder, register block, a decoder, and a gamma transition. The structure ensures that we capture the intricate feature of medical images and enhancing. From the picture on the right, we can see that when gamma is greater than 1, the information of the bright part will be enhanced. And when gamma is less than 1, the texture feature of the dark part will be enhanced. Therefore, after model enhancement, we introduce gamma transformation to further enhance the detailed information of the imaging. The impact of the gamma transition is evident in this compare analysis. Okay, to evaluate our methods, we compare our results with the ground truth. The metric include LNCC, SSIM, and PSNR. Our promise method achieved a PSNR of 29.5, showcase its potential for producing high quality medical imaging. For the discussion, I think there are 2 points that need to be noticed when do this challenge. One is the unpaired dataset, and the other one is domain adaptation. I try to use the pixel to pixel method to deal with this challenge, but the enhancement of the result is blurred. So I try to use the style translation method. Fortunately, it's useful for unpaired tasks. Because of the domain shift, I could add some domain adaptation technology to shrink the gap between the training and test dataset to further enhance the images. None of this would be possible without effort of our team. I would like to introduce Professor Jiang Liu and Dr. He Li, who have been instrumental in guiding this project. Alongside them, Zhong Xiqiu has been pivotal in this research and development phase. So in conclusion, our approach uses unpaired dataset with a G-cycle GAN architecture, hoping that our method could be contributed to medical imaging enhancement. And thank you for listening.
Thank you, Ziqing. Nice play. Next in line is the 1-bit team from Beijing Institute of Technology. They used a SSIM constrained cycle GAN. Welcome, 1-bit. And you can introduce your method now, please.
Okay, everyone, can you see my screen?
Yes, we can see and can hear you.
Okay, wait, let me start my PowerPoint. Hello, everyone. My name is Haonan Han, and I come from Beijing Institute of Technology. I'm very glad to have this opportunity to attend this workshop and present a work on behalf of 1-bit team. The topic of my presentation is ultrasound image enhancement based on SSIM constrained cycle constant adversarial networks. Next, I will introduce a work from those 3 parts. In the background, maybe please allow me to make a short conclusion. That is, the handheld ultrasound equipment is very important in many areas. So I will just move to our method. The challenges commit provide image pairs of low and high quality ultrasound images. The high quality image is the ground truth of the low quality image, but they do not correspond on pixel level. Maybe because of the movable imaging process. two image sources can be represented as A and B. Traditional GAN model can only realize pixel-level correspondence between the different image sources. CycleGAN model inherits the idea of the adversarial training of GAN and adapts the dual training learning method, so that the mapping can be generated from the source to the target without the pair relationship. Inspired by this, we believe that the low-quality ultrasound image can be improved by learning to use statistical text information in high-quality images, so as to improve its effectiveness in the clinical application. The overall structure of our model is shown in this figure. The model we used consist of two generator G, F, and two discriminator networks, the alpha and the beta. The overall loss function of the model is shown below.
Okay, good morning. It's my honor to be here today to share my...
Hello, is there any problem? Okay, let me continue. The second is the cycle loss. The overall loss function of the model is showing like this, and next we will introduce them separately. The fourth is adversarial general loss. It is a loss function used in GANs to train a generator to produce more realistic data samples by forcing a confrontation between a generator and a discriminator. The second is cycle loss. Its role is to improve the consistency and the quality of image generation while reducing detail loss. The above is the basic loss functions for the style conversion using CycleGAN. However, in this challenge, we not only need to completely the quality enhancement, but also need to consider the constraint imposed by the registration work. Since the organizing committee did not release the registration code, we boldly made some assumption. Firstly, we assume that the overall workflow is just like this. That is, a low quality image is first enhanced to a high quality image by enhanced model. The enhanced image are then transformed into a clinical usable image by registration model. Then we assume that the correction model is just a fixed model. That is, each image has a unique correction map. Therefore, the output of our enhanced model not only need to improve the contrast and other parameters, but also need to ensure the consistency of the structure before and after the enhancement. Look at this special example. When we take a freak B in domain B, that is a low quality image that has already been enhanced as the input of the enhancement model. We will generate a new image. The new image should be nearly identical to the input image in terms of structure, contrast, and so on. So we think of SSM loss, which can be used to keep the image consistent. But it is worth to noticing that when we input a real low quality image, we want the information other than the structure information to be as consistent as possible with a high quality image, which is not pixel level matching with a low quality image. For these reasons, we choose the structure evaluation function in SSM loss for the structure constraint as shown like this. Actually, during the challenge, we also try to use NCC and PSNR as loss to constrain the generation, but unfortunately, they did not get good experimental results. During the training phase, we used the training site provided by the committee. Since more organs are included at the same time and the image style of each organ are quite different, we first pre-train our model. In terms of the data size for pre-training, we select 1,050 high-quality image from the official committee's data size as high-quality image, and select several public data sites and provided data sites to form a low-quality image data size, which is also contain 1,050 images. The results of our method are shown in this figure, and the evaluation results are recorded like this. At the same time, we also use evaluation. We also use the evaluate code to. We also show the evaluation results of the original image and the baseline, which is just the original cycle GAN. We can see that our method has a good experiment effect on the original image, and the evaluation index is better than the baseline model. That is all of our work. Thanks to the USenhance organized committee for their help and support during the challenge. And thank you for everyone's listening.
Thanks for your great play, Haonan. Next, as there are two teams unable to join us for time schedule reasons, so we warmly welcome the CDX team from UCLA to introduce their method. They used the cycle GAN with perceptual loss to achieve the goal. So CDX, could you share your method now, please?
Sure. Can you hear me?
Yes, we can hear you.
Thanks a lot. Great. Hello, everybody. Good morning, good evening. This is Team UCLA CDX, and our method is based off of the cycle GAN architecture, and we make use of perceptual loss to make things work. So I'm going to skip over this part where I really intended to talk about why ultrasound image enhancement is important, given that we make use of like tiny handheld devices, which are economically more accessible as compared to the expensive equipment, which is the whole purpose of this like specific challenge being organized, where we could think about some kind of software augmentation to make sure we could translate low quality images into high quality images at basically no cost. So our contributions are as follows. So we start by, or the major contribution is integrating perceptual loss for quality enhancement. And to be more specific, we make use of the LPIPS, which is the learned perceptual image patch similarity. And we inculcate that into the loss function. And this helps promote human perceptual quality in image enhancement as compared to like other traditional metrics like the L1 loss or the MSE loss and things like that. And the other modification or the other contribution that we do is making a tiny modification to the enhanced cycle GAN work by Huang L. And we make a change there by adding more residual blocks to the generator's architecture, and that does provide a significant performance boost. One important aspect that I would love to like highlight at this point is the promising test set results based off of like not making use of like high quality test set information during model training or validation. So these are the scores. These scores have been picked from the challenge leaderboard. In general, cycle GANs are pretty ubiquitous when it comes to like image-to-image translations. They are primarily used in the applications where it makes sense to use unpaired training data in order to like help the model learn the translation between the two domains. But in our case, given that we were provided with paired training image samples, we intended and we decided to make use of those paired samples in order to complete our model training. So I'm going to quickly go over the model overview. There are a bunch of slides that go over that. So we initially begin with our low quality and high quality input training data set. So this is the data set that has been provided by the organizers. These images are by definition not registered, and we just make use of these input scans as is. And we pass them to like two generators, generator high and generator low, which translate low to high and high to low. And both of these happen parallelly. And they result in H prime and L prime, which are the quote unquote generated images. And then we make use of these figures to pass them to the other generator here to produce L bar and H bar, which are the outputs of the entire CycleGAN framework. And we make use of these outputs and compare them with the input low and high image pairs to using the discriminator to provide outputs based off of that. And we make use of the discriminator's output to compute our adversarial loss term. And we make use of the same pair of images, the low and L bar and high and H bar, to compute our cycle consistency loss. And this is the new loss term that we introduce as compared to the original paper, where we make use of H prime and H and L prime and L to compute the perceptual loss. And as usual, we also make use of L, and we pass it through the same generator to compute the identity loss, and we repeat the same for the high quality set as well. A quick look at the generator architecture. This is pretty close to the paper by L. Huang in 2022. The only difference, or the only significant modification, being the use of 15 residual blocks instead of the usual 9 that all CycleGAN papers use. That's the modification. And the discriminator architecture is largely similar, so we keep it consistent. The loss function here would have like 4 terms instead of the usual 3 terms. We have the adversarial loss term, the cycle loss, the identity loss, and the perceptual loss terms. We add all of them and we do a weighted sum of all of these loss terms to compute our overall generator loss. Each of these loss terms, I'm going to quickly go over what they're composed of. So the cycle loss is essentially a L1 loss between the original high quality image and the ones that has been generated by passing the high quality image through a low generator and a high generator. And the adversarial loss is simply the loss that we compute based off of a mean squared error term between 1 and what the discriminator thinks is the correct class, or if based off what the discriminator thinks if the image is like real or if it's fake or generated. And we also have the identity loss term, where we make use of the L1 loss to compute the difference between high and the high quality image that goes into the generator and that's spit out by the generator. The perceptual loss term is interesting in the sense that we make use of the VGG16 architecture, and we pick up features from multiple layers of the VGG16 architecture, and it computes a weighted sum of each of these features of the L2 difference between the features for each of these input images, and then we add them together, and that weighted sum is what computes or what provides the LPIPS loss. And we compute this loss for both the high and the low pairs, and we add them together, and they both have same or equal weightage in this case. So these are some validation set results. The top row shows the low quality input images that were provided to us. The bottom row shows the high quality stuff. And in the middle row, we speak about the outputs of our model, and we could clearly see that the model tries to tend to learn the difference or the domain difference of increased intensities and things like that as a distinction between the low and high quality image pairs. But we would also notice that given that the low and high quality images are not registered, the model fails to learn how the registration process might have helped. So these are validation set performance during the CycleGAN training. I have this here just to just to reemphasize the fact that training the model for an increased number of epochs does help with improving validation and test set performance, but also training the model for more epochs than what's needed is just wasteful in terms of resources, and it also doesn't provide a significant boost in model performance as well. These are some references that we made use of, all the 4 papers that belong to the organizers, the challenge organizers, and then some other papers that we made use of while coming up with the solution. And that is probably everything from my side. Feel free to contact us, Professor Spear, who's probably here in this meeting. He leads the team, and I am Sriram, and I am the primary contributor to this project. Thank you so much.
Thanks.
The top 10 winners. The top 4 to the 10 goes to the TJI Lab from Tongji University, IMAT8 from Southern University of Science and Technology, and one bit from Beijing Institute of Technology, Stoke Parker from Central South University of Forestry and Technology, .Pi from Beijing University of Technology, CDX from the University of California, Los Angeles, WRC from Lanzhou University. And our third place award present to the IMAT8 from the Southern University of Science and Technology. And our second place goes to the NCIA from Seoul National University. And the first prize goes to the POAS from Pohang University of Science and Technology, and the University of Ulsan College of Medicine. Warm congratulations to the top 10 winners. So later we will release our data set, and by releasing the data set, running the online server and holding the challenging tasks, the ultrasound enhancement 2023 is expected to attract more attention from the research communities and advance the research on high quality ultrasound images significantly. That's all for our workshop. Hope to see you in the next MICCAI. Thank you.